In section 2-6, we're looking at the quadratic formula. You likely remember it from that lovely ditty, x equals negative b, that song, you know, when you were solving in Math 2 and taking a quadratic formula and filling in all those lovely formulas, as you'll see here down at the bottom. The first question we want to look at is how many zeros or x-intercepts can a parabola have? If we look at the graphs of them, remember zeros or x-intercepts where it crosses the x-axis. If we take a look here, we can see this one, the red one, crosses 2 times, the blue one crosses 1 time, and the purple one doesn't cross at all. Therefore, we would say a parabola can have 3, 2, or 1 intercepts. Let's change that font there, 3, 2, or 1. Knowing that, and we want to find those intercepts, there's lots of ways we can factor. Now, you may remember the quadratic formula, and you might remember the song, but what does it actually find for you? Here we have an equation, 3x squared minus 5x minus 8. We've identified our a, our b, and our c, and they plugged it into the quadratic formula. You may want to pause this video to make sure each step makes sense, and I recommend you're careful with the signs. When we get done, we're solving and we find the answer for x equals 8/3 and x equals -1. Notice on the graph, that is where they cross the x-axis. So basically, the quadratic formula will find for us the x-intercepts of a function. Now, we must let you know about Franny the festive factor fairy. She loves to factor. So the quadratic formula is fun and all, but she would like to factor on the side if possible to show you that you get the same answer. She has taken this same equation from the last screen and factored it here. We'll notice that she too got the exact same x-intercepts or solutions to the quadratic equation. Watch for her on future slides. Now, in the quadratic formula, there's something called the discriminant. It's the part under that square root, the b squared minus 4ac part. This is going to help us predict what type of zeros or intercepts a function has and how many there are. Let's take a look at some examples. The first problem we just did, where Franny factored for us, and we actually did the quadratic formula, here it all is again, we found our solutions to be at -1 and 2 2/3 or 8/3. This 121 in our square root, the discriminant as we're calling it, is a perfect square. When it's a positive number, 121 is positive, and it's a perfect square, it tells us that we have 2 real rational roots. Now we look at another example, and again, you may want to pause this video at any time to watch the quadratic formula work and be sure you know how every number is plugged in. This one, we have the discriminant. When we get done solving b squared minus 4ac, we have a 0. So the square root of 0 is 0. It basically vanishes. Therefore, we have -12 over -8, and that's 3/2. Note what that means on the graph. We only have 1 root. It's a real number, 1.5, and it crosses the axis only 1 time. We could also check out Franny the factoring fairy. She found the factors match each other. It'd be 2x minus 3 times 2x minus 3. When she set them equal to 0, she got 3/2, which also matches our 1.5 x-intercept. Now we have another example, and we've plugged in our a and our b and our c. Remember, our a here would be 1, our b here would be 6, and our c would be 3. We follow the quadratic formula, and note here that 24 is positive, so our discriminant we would say is positive, but now it's not a perfect square. That's okay. It still tells us we have 2 real solutions or roots on the parabola, but they're irrational. That means the number goes on forever, kind of like pi. So I have continued down in solving the quadratic formula. Right here, super important that you are able to reduce that root 24 to 2 root 6. Remember, that comes from over here on the side, the square root of 24, when we practice reducing our radicals, that would be 4 times 6, but the square root of 4 is 2, that's why that 2 came out front, and the 6 stays in the radical. Also, make sure you reduce all of these terms in the front. The coefficients out front can be reduced by dividing by 2, and that's how we get -3 plus or minus the square root of 6. If you type that on a calculator, you'll get some lovely decimals. They'll go on forever. That means they're irrational. That is where the parabola crosses the x-axis. Note how sad Franny is. She was unable to factor this one, and that's because that discriminant was not a perfect square root. She now realizes, while factoring is important, it can't solve all the quadratic equations. That's why we must have the quadratic formula. One more example, we try the quadratic formula and we get the square root of a -16. Now this brings into view that idea where a square root of a negative used to be no solution. But you're all aware now that square rooting a negative just brings in our imaginary numbers. So because we have a negative discriminant, it will tell us there are 2 imaginary roots or complex roots. Look at our graph. It doesn't even cross the x-axis. So we used to say there's no x-intercepts. Now we just say it has 2 complex roots. As I continue down here, you'll notice that 16, remember the square root of 16 is 4. That's why you see the 4. And the square root of -1 is I. That's why you see the I there. We also could reduce all of these first coefficients by 2. So our final answer is 1 plus or minus 2i. One thing to note, Franny's still sad because not only was the square root not perfect under the discriminant, it was a negative. She was really sad. To summarize it all up, if your discriminant, the part under the square root, is greater than 0, you're going to have 2 real roots. We did note that if it's a perfect square, those roots are going to be rational or having an ending decimal. If your discriminant equals 0, you're going to have 1 real root. That parabola will just touch the x-axis 1 time. If your discriminant is less than 0, it will have 2 imaginary or complex roots. This is a super key slide. You'll want to refer to these notes when working through problems. Now, we've done a lot of notes and different ideas. Your packet has 2-6, lots of quadratic formula. All of these problems reuse the quadratic formula. I would recommend trying them and checking for your teacher's answer key. Quadratic formula, quadratic formula. Notice how they're all equal to 0. Now, one of them comes up with 2 different methods. You can kind of see either between here and the packet of the answer key that we tried the quadratic formula because it was equal to 0. But another method you can do is that factoring by grouping. Franny's back. She's excited. So we would say we have our 6x squared. We want to do our times to the top thing. So we would multiply our -20 times 6x squared. And we'd have -120x squared. And the bottom we would have our 7x, or -7x. And we need to multiply things to multiply to -120, but add to -7. That's going to be a -15x times 8x. Now we go back and we rewrite our first term, 6x squared, and our last term, -20. And we write our middle terms. You can put them in any order, but I'll do -15x and plus 8x. When we factor by grouping, we put the 2 first ones at the table together. They both have an x in common, and 3 goes into both of them. I'd have 2x left inside if I'd multiplied back together, and a -5. Then I'm going to group the next set together here. So I'd have 8x and -20. Remember, whatever the sign is, I keep it the same, plus 8 and -20 both have a 4 that goes into them. So that'd be times 2x to make 8x and -5 to make my 20. This was the cool part, that you have the same thing in the parentheses, 2x minus 5 times your leftovers of 3x plus 4. Now, remember, we need to have this still equal to 0, just like it was in the beginning of the problem. We would set 2x minus 5 equal to 0. And by adding 5 to both sides, I'd have 2x equals 5, and then divide by 2. X equals 2.5. Hey, that's the same answer as we got over there if you look at the quadratic formula. And also 3x plus 4 equals 0. Subtracting 4 and dividing by 3 would give me x equals negative 4/3. There I would have the same answer. But wait, Miss Berklin's not going to start over. I apologize, guys. Let's take 7 minus 23 real quick again. That's going to be negative 16. And over 12. Yikes! Let's turn that arrow around. If we reduce negative 16/12, we get negative 4/3. That's the same answer that factor Franny got. Good thing we had her there to check for us. So both those methods will work. There is a try it in the packet. You could go ahead and try that one with both methods. You can see which one you prefer. There's a lot of graphs and some blank tables in there, guys. They're just going to have you graph these with the key features. You could use Desmos if you like, or think about the y-intercept in the vertex form. Basically, you're going to try that quadratic formula and use your discriminant to decide what kind of zeros it will have. Is your discriminant negative and they're imaginary zeros? Is your discriminant positive and it's 2 real zeros? Or if your discriminant is 0, remember you would have 1 0. There's that note on discriminant. We kind of talked about that already. These ones, you actually only have to do that b squared minus 4ac. Kind of gives you a shortcut. So you would just do the b squared minus 4ac, and depending on what type of answer you come up with under that radical, you'd be able to answer what type of roots it has. Check your answer key again to see the solutions. Finally, there's a story problem here, and they give you the height of a tennis ball modeled by this h of t equation. They ask, will it ever reach a height of 4? So I set it equal to 4, and again, you can catch this answer key in your teacher's packet online, and I wanted to solve it. So my best way to do that was to subtract 4 from both sides, and now I will use the quadratic formula to solve this. But I actually just decided to do the b squared minus 4ac part. And when I did that, I got the square root of negative 15. That means 2 imaginary or complex solutions. There's no real solution to this problem, which was related to the story problem, asking if it ever hits 4 meters high. Therefore, without doing that full quadratic equation, I could tell that the ball never went to a height of 4 meters because my quadratic equation had a discriminant that was negative, so there was no real solution.